Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, we're very happy that before leaving, Tobias agreed to give us a second version of the talk he gave at the University of Washington earlier. So let's hear about quasi-random load balancing.
Thanks, Yuval, for the introduction. So I've been here for 2 weeks. That's my last day here at MSR. And I'm going to talk about quasi-random load balancing. I hope, the title somehow will explain later. Okay, so since I have seen too many conference talks where I didn't get the problem on the first slide, I tried to make a visual start to the problem of load balancing. So given some compute cluster, which is some network, and we have a number of tokens. This is kind of, you can also call it load or number of chips, somehow arbitrarily distributed over your network. And what's your aim? You want to somehow balance it out. So this is kind of the jobs you have to handle, and you want to balance it out such that every processor or every node of this network has roughly the same number of tokens. Okay, and to make that easy, one can assume that load is divisible, which means you can split it up in arbitrarily small pieces. Then this becomes kind of simple. So let's look, for example, here what happens if these 4 tokens divide. Well, they split, they split, they split. Here you see they split in halves, and there, well, half of the difference is sent to the neighbors. This was like one time step. You balance out with your neighbors. And in the next time step, the pieces are getting smaller and smaller, so we get some distribution like that one. So you have 1.5 tokens here, 1 3/4 here, 2.5 here, and so on. After another step, just to finish that up, you might have distribution like that. And after, say, a logarithmic number of time steps, n is the number of nodes. If this was an expander, meaning that you have some constant eigenvalue gap, then this is perfectly balanced, meaning the discrepancy, the difference between the maximum and the minimum load is a constant.
So how exactly do you balance out the load? In each step here?
A formal definition comes in the next slide. So this is the problem we are dealing with. You have some distribution of the load, some arbitrary distribution on your network, and you want to balance it out equally up to some small constant. Okay. Here comes the definition Yuval was asking for. So we assume we have a connected, undirected graph. And to make the talk easier, I say the graph is regular. Otherwise, if it's not regular, this is just the maximum degree. And this is the diffusion matrix telling us, well, we keep half of the load to ourselves, and the rest we split evenly and send it to our neighbors. So if we have degree 2, then, well, we send a quarter to each of the neighbors and keep half to ourselves. Okay. So we stay in the idealized case where everything is nicely divisible, and then we say, okay, at every time step, we have some distribution of the load, which means at every time step, this is some vector, some real vector with dimension number of vertices. And what happens in one time step? Well, the new load vector is the load vector times our diffusion matrix, which means that at time t, we have the initial load times p to t. Okay, so that's a very easy chain if everything is nicely divisible. And what are we actually sending on a fixed edge? So on the edge from vertex I to vertex j, what are we sending? Well, it's the amount we are sending from I to j, depending on the load at I, minus the amount of stuff we are sending from j to I. So that's what we are actually sending. That's the flow on an edge ij. Okay, small example, just to make sure that everybody knows the model. We have two vertices of degree 4 with load 16 and 2. So here we want to send 1.75. Since the load difference is 14, divided by 2 is 7, divided by degree 4 is 1.75. So that's what we want to send here. And if everything is nicely divisible, then we send exactly this. OK, that's the model. And now we are coming to the more realistic case. Since in real world, you can't split up your jobs in arbitrary small pieces. In the real world, your jobs are discrete, which means, well, you either solve this problem or you don't. You can't split it up. So in the real world, you can't split up your tokens. Well, then it becomes a bit more interesting. So the question is, well, how do we discretize this divisible flow? So that's what we used to send in the continuous case, from one vertex to another one. Well, the first thing you would come up with, I suppose, is this approach of rounding towards 0, which means just rounding it down. This was suggested by Rabani, Sinclair, and Wanka more than 10 years ago, 12 years ago. And looks as follows. This is what we want to send in the continuous case. We just round it down. So this is the integral flow on an edge. Let's look at our example again. We wanted to send 1.75. We round it down and just send 1. That's the.
I assume that this is the direction where it's positive.
Yeah. And we can now describe our process again with equations, which means, well, the new load is the old load minus, well, this what we are sending out. That's the flow from I to all its j neighbors. And using this Eij, this is the last notation I'm introducing, is the difference between what we are sending in the continuous case and what we are sending in the discrete case. So this is kind of the excess we have because of the rounding. So because of this, we can't split our tokens arbitrarily. Well, we make this kind of mistake. So this is the excess load allocated because of the rounding. And if they have this notation, well, then apparently here the excess is 3/4. So we round down by 3/4. And we can describe our process as, well, it's what we would have done in the continuous case if we could have splitted it, plus, well, summing up everything what we didn't because of the rounding. So that's a simple equation. And you can analyze this. OK. And now comes Claire and says, randomness is the salt in algorithm design, something like that. So now the obvious question is, yeah, rounding down each time we have 1.75 to send feels like a waste. So if we actually want to send from here to here 1.99, rounding it down, come on, this can't be the fastest way. So well, the natural randomization would be a randomized rounding, saying this approach, which means we choose the integral flow as a randomized rounding of the continuous flow. So not just always rounding down, but doing a randomized rounding. Randomized rounding means, well, if we have our rounding example of 1.75, rounding up with 1/4, rounding up with 3/4, rounding down with 1/4. So rounding depending on the fraction part. OK. And well, this has some nice properties. So we see that the expected flow is exactly the continuous flow. So in expectation, we're doing exactly what we do in the idealized model, which is like, well, the fastest and quickest you can do, splitting up everything as good as we can. And what do we have as well? Well, this excess, the expected excess, so what we do wrong in expectation is 0 as well. So that's kind of, well, hard to, I mean, that's like an expectation we are doing optimal. Well, if we use randomization, first, it's harder to analyze. And second, in this case, it could happen that you send out more than you actually have. So if, like, on every edge, you want to send out, in the continuous case, 1.5, and since you round independently at random, round up everybody, then it can happen that you round up every edge and send out more than you have. So you might end up with negative loads in the middle. But, well, that's not too bad, so you can handle that. But, I mean, there are some issues with this randomization. But, well, it's a nice model anyhow, I believe. OK. But now, after we have regarded Claire's talk, we get back to Jim's talk about quasi-randomness. Now we see we have a random process where we do this randomized rounding of the continuous flow. What's the crucial property here? The crucial property is that the expected excess, so the expected rounding error I make, is 0 or is small. So what we actually want to achieve with our randomized rounding is that these accumulated excesses, so like that when we round, we don't always round down and always send something less than we actually should be, that this remains small. So let's look at the following de-randomization, or at the following model, bounded error diffusion. I say we choose the integral flow such that these accumulated rounding errors, so this is summing up these e's over time, are small, which means I look at an edge and I watch out that not every time I'm rounding in one direction. So I want that these roundings are, well, if they are too much in that direction, then next time I should round in the other direction. So I somehow want to bound these errors. And well, then of course I can define this excess as continuous versus discrete. And our running example, we want to round the 1.75 as we are used to. We want to have, say, to keep these accumulated rounding errors below than 1. So say this is 1. So now we have to decide whether we round this 1.75 up or down. Well, if we round it up, we have an error of 1/4. If we round it down, it's an error of 3/4. So we can say we round it down, which means we choose to round it down and get an error of 3/4. In the next step, well, again, we want to send like 1.5 in the continuous case. So, well, now we have already rounded down by 3/4. If we would round down again, we would add up a bias in the other direction of accumulating these excesses up to 1.25. So we have to round in the other direction, so we have to round up this time such that we have a negative excess, and this sum is just 0.25 and not 1.25, so that this stays smaller than 1. So that's the rule. OK, that's a very general framework, because I didn't tell you how I actually choose how to round. And, well, I guess you already have an idea how you can do that. I call it quasi-random diffusion. We can discuss after the talk whether you like the title or not. The easiest way is we say we round up or down such that this accumulated rounding error is minimized. And I call this quasi-random because it somehow imitates this property of the random process of having a small accumulated rounding error. So that's what it somehow imitates deterministically. And, well, this corresponds to a bounded error diffusion algorithm of the previous slide with keeping it below 1/2. And it can be implemented with log of the degree storage per edge. And I call it quasi-random. I already excused or explained that. OK. Now to the results. It's slide 22, so a bit late for that. Well, I want to show the models first. So we just look at two graph classes. The first one is the Hypercube. You know what's a Hypercube? And for the Hypercube, it's known that for this idealized process, where you can split up your jobs in arbitrary small pieces, you can reduce a discrepancy of k down to a constant within log times log number of steps. And now what you usually do is you compare how much the discretization makes things worse, makes them slower. So we want to compare the deviation at all times, at all vertices, between the idealized process and the continuous and the discrete process. And it's known that for this deterministically rounding down, this is a log cube.
This discrepancy of time, so can you remind how you measure discrepancy?
This is the difference between the minimum and the maximum load. Okay, so we see that, okay, our deterministic process is pretty close to the continuous process. That's what we want to compare. Now we introduce this randomness, which means we don't round down all the time, but we sometimes round up as well. Then with high probability, we get a bound of order log square. So by introducing this randomness, we get slightly better. And now comes the title. If you remove the randomness again, then you get even better. So here you see that's the standard deterministic rounding down. This is the randomized rounding, log square. And if you do this bounded error diffusion or this quasi-random, keeping the accumulated rounding error small, you get it down to a log.
Can it be faster than the idealized one?
This
is the difference. So this is measuring two things. This is your number of steps. So this is what you need. I mean, you can't avoid to do. Takes at least as long. And here we just compare both processes. So I just added this first item that you can match it to, after that time, you have that discrepancy result.
As long as the final answer is integer, why does it matter that intermediate steps are fractions? Because you have intermediate steps with negative numbers, which are not obviously better than having fractions.
Yeah, but I mean, if you have a certain job and it's send it around in your network, what does it mean to send half of a job?
It's a computational step. I thought you compute until the job goes where it goes and then you start.
No, I actually send it. So in each step, it's really send, and then the load is different. And I want that this process, which is somehow guided by this local looking how the rounding errors on my edges, that this converges fast globally.
Then you need to fix for negative number of jobs.
Well, this negative thing is not so bad since well, you can just add some virtual tokens which have no real load, and you're close enough to the idealized that you don't get in the negative range then. But people seem not to bother too much about this negative problem. But of course, I had to raise it since I'm about to sell the last one. Claire?
So I could come up with other suggestions.
Of course, there are various other ways of randomization, and there are various other ways of quasi-randomization. So like rounding down on all your edges, and then look at how many tokens remain, and distribute these guys at random or in some cyclic order, or there are loads of ways one can think of. But you still have to be able to analyze it. That's the other thing. I mean, we can discuss other models. Okay, so this was the behavior. Yeah.
So, sorry. So this log n, that's kind of so that's nice. So that's why this is the right particular way of doing it.
Thanks for asking this. So in fact, this is theta for this algorithm, and I don't think you can do better. And since I'm an honest person, I also tell you what's the lower bounds here as well, because it looks really nice with O log cube, O log square, O log, but actually the only thing we could prove here is an omega log, and well, at least here you have a provable gap of omega log square.
I'm missing something just on the initial intuition. So this, when you do the idealized thing, it's like the distribution around the walk.
Mm-hmm.
So n here is this, not the dimension of the cube, it's the number of vertices.
Yeah. Yeah.
Okay. And But
So this is basically d cube, d square, if d is the dimension. But I want to avoid this this d because it's somehow arbitrary, whether it's dimension or degree.
how does this? So it looks like the idealized thing is just the distribution of a random walk started
Yeah.
here.
Yeah.
And somehow the random walk and the hypercube mixes in time log n, log n. So where is? But that doesn't seem to correspond to what we have there. So.
Well, you have this initial discrepancy as well. And as long as this is a polynomial, you have a log square as a bound for the time until the continuous process reaches the constant between the maximum and the minimum load. So that's like classic. I'm just working on the deviation. I mean, whatever bound you have on the idealized process, I can tell you, well, I have the same plus this deviation.
But this one is sharp, the one for the idealized.
Yeah.
I don't understand. Why doesn't K get into the expression in the quasi-random? I mean,
Well-
I don't know. I take K to be, n to the n to the n.
Because it's rounding, so large, it doesn't scale because it always have an integer.
Yeah.
Why does that matter? I cut the amount of math that is in
But this is
some
the
point.
error between the idealized and the rounding.
So here.
Realize has K in the expression.
Right, but the error, this is the difference between them.
Yeah. We are talking here about the discrepancy, which is here k versus a constant. This runtime here, well, it doesn't appear here at all. I don't care. I just measure what's the difference at all times between the two processes.
This is the latter things are not times; they are.
No, just the discrepancy, which means the difference between the minimum and the maximum load.
I'd like to suggest another process, but I don't want to.
Yeah.
I mean, I don't know how we should handle that. So, I like to discuss other processes. But,
Let me try to do it quick.
okay.
Your two vertices, neighboring vertices with 16 and 2. You average and you said, okay, you should send 1.75 from left to right. How about keeping them separate until after you've done the discretization? So you said the 16 wants to send 2 to each neighbor. Okay, so that's 2 going from left to right. And the 2 wants to send 0.25 from right to left. So how is it going to send 0.25? It can, for example, do it in round robin. Send one time north and next time east and so on. And then you make the difference.
That's a very nice protocol. I'm going to analyze in the summer or something. But the problem is that all these protocols, it's kind of crucial that you have an edge-based view. So edge-based view. So what you are saying, you have a vertex-based view.
Right.
So that the vertex decides, I'm sending this amount, he's sending this amount, and then, well, the edge just sends the difference. But these techniques are somehow bounded to an edge-based analysis. Okay, but I wanted to sell another graph as well, which is similarly simple, which is the torus, a d-dimensional torus with d is a constant. Well, it's known how fast the idealized process gets down to a constant. And again, we are only interested in the deviation between the idealized and the discrete process. And it's known that it's a polynomial for the always rounding down. It's also a polynomial for this randomized rounding. However, it's a constant for this quasi-random approach. And well, this constant, of course, is sharp. Here you can prove a law bind of some polylog, and this is sharp as well. So here you have a provable gap between these two guys. Well, not a provable gap between these two, but at least this is a huge gap between a constant and not a constant. Okay, so now we have hopefully understood what's the model, what's the problem. And now we want to see how do you prove something for these models. And first I want to say my favorite lemma. It's very simple, very easy to state, easy to prove, and very handy. So I think I had 4 or 5 papers where I used kind of this lemma. So what does it say? Well, you have some function mapping from x to r, and you have some, well, so that's the function, and it's unimodal, which means going up, going down. And you have these x's, x1 to x14, some fixed points, and you have some sequence plus minus, so like assigning each of these guys plus minus, and then it's easy to see that this sum can be bounded by twice the maximum. Well, and why? If you split this unimodal function at its local extrema, then, well, this is the sum of the left guys, which is, well, this minus this, which means I just add up these stripes. So the whole sum on this side is bounded by the maximum of the function, left and right. So this is why you get a 2 times maximum. It seems to be a well-known lemma. It's somehow not that often used, but you can generalize it a little. By the way, if you have a good citation for it, I would be very open to hear. Okay, you can generalize it a little to, well, L modal functions. So if you just have L extrema, then, well, it's basically the same. And you can also generalize it not having this plus minus 1 sequence, but having some sequence of this factor here, which has partial sums which are small. And then you can bound this, well, if these partial sums are bound by lambda, then you can bound the sum by maximum. And I mean, this is kind of nice, because if you know that your function is unimodal and you have these coefficients which have these small partial sums, then a sum becomes a maximum. And the sum usually is much larger than the maximum. So this is a very good bound if your function is unimodal. Okay. Well, that's my favorite lemma I want to sell. Now let's see how to apply it.
It usually goes under the name summation by parts.
Yeah. Okay. And now we want to see how to apply that for the hypercube. So we have some discrete process where these accumulated rounding errors are bounded by some lambda, and we want to prove that the deviation is at most a lambda times log n. Okay, we can describe this deviation between the idealized and the discrete process by this sum. I'm not going to tell you why. It's, well, summing over the time, summing over the edges. Then here we have this excess, and then this is the probability of going from 0 to I minus going from 0 to j. And, well, you can bound this by 2 times this sum, just bounding it. And now we see something which looks familiar. So this sum, actually, we want to apply our favorite lemma. Because we know that these partial sums of these coefficients are small, by assumption. And, well, if we also would know that this guy here is unimodal, then we could say this sum becomes a maximum, and then some combinatorics would give, well, 8 times lambda times log. I mean, then I have to know what's the maximum of this probability, but I can bound that. So the main problem here is to say that this probability here is a unimodal function, which looks like should be known. And I mean, we discussed this issue. And OK, so it remains to prove that the probability of going from 0 to I in this hypercube is unimodal in time. And, well, we can describe this as follows. We know that Pij is the probability of going from I to j. We now introduce Fij as the first passage probability, saying this is the probability that a random walk started at I goes to j, is at j the first time at time t. So that's the first passage probability. Well, at a random walk starting at j visits j the first time at step t. Okay. Then we can describe this Pij as a convolution of, well, to go from I to j is the same as going from I to j being at j the first time, times, well, doing arbitrary number of loops at j. So that's an easy observation. And, well, this guy is obviously unimodal. So going from j to j is unimodal in time. Why? It's monotone. Since, well, in 0 steps, I'm with probability 1 going from j to j. In more steps, the probability is getting smaller and smaller.
So this is just for the lazy random.
Yeah. Yeah, that's important. And, well, if this guy here is log concave, was log concave, then, well, convolution of a unimodal and the log concave function is unimodal again. So it remains to prove that this first passage probability going from I to j, the first time at j, is log concave. Okay, so it remains to prove that this first passage probability is log concave in time. Now we can observe that so far we looked at random walk on the hypercube, but, well, a hypercube just consists of certain layers depending on the number of ones in the vertex. So you can describe a random walk on a hypercube as a random walk on a path, just with adjusted probabilities of going backwards and forwards. So this is basically the same as a random walk on a path with appropriate probabilities. So it remains to prove, we heard that a couple of times, that this first passage probability on a path is log concave. Okay, then we have a very classic result of Carlin McGregor, which is, by the way, the father of Anna Carlin from UW. And he proved it for the continuous case, and Phil recently proved it for the discrete case as well. So one knows that the first passage probability is distributed as the sum of independent geometric random variables. These guys are all log concave. Convolution of log concave guys is log concave again. So that's done, kind of. Well, we can prove it ourselves as well. And because, well, this paper just came out 2 weeks before our work. So I just sketch you, I made it a bit shorter, how one would prove it if one wants to prove that this first passage probability is log concave. So first we observe that if we want to go from 0 to d on a path, it's the same as going the first time from 0 to 1, first time from 1 to 2, and so on. Then we can do a Z transform and get to a multiplication of these probabilities. And now we can just look at these probabilities and see where their roots are, and then we get an expression which is some constant times this guy. And if we look at this guy long enough, then going backwards gives the geometric distribution with the right parameter, and now we have a convolution of geometric distributions which are each log concave. Convolution of log concave is log concave, so this probability is log concave. This was the proof for the hypercube.
So, you can't write a formula for PIT?
Well, you can, but you don't see interesting properties. Thanks that he says this. So, yeah, so one has to do a bit more. I thought it must have been known before, and this probability is log concave, but I come back to this question later. Okay, so we have seen how it works in the hypercube. Now we want to do the same on the torus.
Do you think it's unimodal on any transitive graph?
Wait for my last slide, please. Okay, so how would you do the same on the torus? Just a quick sketch. So again, we want to prove that the deviation between this continuous and this discrete process is, if it's bounded, then our deviation is small. Okay. So again, we start with the sum of this excess times the probability, and now we have a random walk on a torus with loops, a lazy random walk. We can describe this lazy random walk with loop probability 1/2 on a torus as a random walk without self loops on a 2D dimensional grid. So like if this is your torus, well, then you mirror the torus in all directions, so you become a d-dimensional grid. And now you have this self-loop probability of 1/2, where the d extra dimensions do the job, that you just map them to the same point. So you can describe a random walk on a lazy random walk on a torus as a non-lazy random walk on a double-dimensional grid. Now we have these probabilities p bar for the 2D dimensional grid.
But the torus wraps around itself, but the grid doesn't.
Where the grid is infinite, I simulate this on the grid by wrapping the torus like this and again, so that like if the grid walks here, then on the torus it's the same point. So the probabilities of the torus are sums of positions in the grid.
Why are you doubling? The torus is d-dimensional?
The torus is d-dimensional, and I need a 2D dimensional grid to have well, this loop probability of 1/2 incorporated. So these d extra dimensions I just ignore, which doubles the probability of staying there. Okay, so we basically can bound our deviation now by this sum, but this just got a non-lazy random walk on the grid, which is much easier. And there's this beautiful book by Lawler. He also has an updated version on his homepage. Very, very good book. Where there are nice local central limits theorems which say that, well, this probability of a random walk go from 0 to I on a d, or in this case 2D dimensional grid, is roughly this multivariate normal distribution, up to some small errors. And, well, this means this expression is basically this multivariate this normal distribution plus some small error. And then comes handy this nice proof by Cooper and Spencer for these deterministic random walks. We used a similar approach, and they already showed, so we didn't have to do that, that this difference actually just has 6 local extrema. Well, now the favorite lemma comes into play. We apply our lemma. Can bound this guy here. Well, we also have to bound this O of small, but one can do this, and finished with the torus proof. Okay, to sum up my open problem for you, for which other graphs is the transition probability between two fixed vertices unimodal in time? For the sake of safety, I mean a lazy random walk. And as we have seen for the torus, we needed some approximate unimodality, which meaning it's very close to unimodal function, but so close that the sum of these errors is still small. I mean, this holds for the hypercube and for the torus, and maybe one can show similar things for random graphs or random regular graphs. I tried that, but so far no success. I believe it's something more general, but
that it's unimodal on the torus, right?
No. Well, it's somehow hidden in the approximate. It's k constant modal.
The limit is. But then the error has 6 extremes.
It's not purely unimodal.
Yeah.
Because it's small.
Yeah. This is what I mean with approximately. And
do you know that it's not actually unimodal on the torus?
I don't. No, I don't. I know that this also holds on a regular tree.
But on the continuous dynamic one, it's slightly more natural.
I mean, I leave this as an open. I mean, it somehow always felt to me that it should be known for other crops, But that was apparently hard enough to show it for the Hypercube or approximately for the torus. I mean, this would immediately give bounds for this quasi-random load balancing, but it's an interesting question on its own. I believe.
Okay, so what you showed was a little more this log concavity for the just the unimodality, I guess, just the unimodality is easier, and we have it in the paper from a couple of years ago for birth and death chains, which implies it for unimodality.
For
unimodality for birth and death chains, and then it implies the Hypercube case by the same thing.
For the Hypercube, it applies, yeah.
But there we didn't do any log. We didn't discuss the log concavity
because it just needed the unimodality. Where we needed the log concavity to have the convolution.
Yeah, this was the unimodality directly of P.
Okay. Because log concave convolution unimodal is unimodal, but unimodal is not unimodal. Okay, so thanks for listening. Jim, you had another question?
Yeah. So you said another. Is that like a hint that I've asked?
You didn't.
So one important feature of the Cooper-Spencer results is that they're limited to bipartite graphs, and that's important technical level. Something I've never understood, by the way. Now here, it doesn't look like you're using the bipartition. In fact, you're doing the lazy walk, which suggests that that's not important. But all your examples are bipartite.
That's a big difference to these deterministic random walks, because there you have a problem with the bipartiteness. We can discuss about that later. But here this is resolved by the laziness. So the lazy part saves our day here. And so that's important. Otherwise, on a bipartite graph, it's always 0, 1, 0, 1, or larger than 0, 0, larger than 0. So with a normal random walk, you are lost with that probability. With that property of the probability without laziness. But one could still use parts of their results.
But this should apply, as far as you can tell, to other graphs that are not bipartite.
Yeah. But the examples were too simple to have non-bipartite guys. Okay, other questions? If not, then thanks again.